Previously, we have discussed the statistical methods to compare two population proportions and to estimate the difference between two population proportions. In this video, we will discuss a statistical test that can be used to compare multiple population proportions when the number of populations is 2 and above. This test is known as a chi-square test. Chi-square tests have a wide range of applications, not limited to comparing multiple population proportions, as we will see in the later videos. In this example, we would like to test whether a die is fair or not. To do that, we first roll this die for a total of 300 times, and recorded down the number of times that each of the 6 sides turn up in a table. This test is to see whether this die is fair or not. It may appear that it has nothing to do with comparing multiple population proportions. But let's write out the null and alternative for this hypothesis test first. In general, the null is a statement claiming that there is not any effect going on, whereas the alternative is a statement claiming that there is some kind of effect going on. Having no effect means this die is fair, under the context of this example. Having an effect means that this die is biased or not fair. We're going to use P1 to denote the probability that this die turns up on side 1, and P2 to denote the probability that this die turns up on side 2, and so on. If this die is indeed fair, we would expect P1, P2, all the way to P6 are all equal. This die should have the same probability of turning up on any of the 6 sides. In fact, we can figure out this exact probability to be 1 over 6, because there are 6 sides in the total. So the null should be all 6 probabilities being 1 over 6. The alternative, on the other hand, would be one of the 6 probabilities being different from 1 over 6. It is important to know that we do not need all of these 6 probabilities to be different from 1 over 6. We just need one of those 6 probabilities to be different from 1 over 6. It is worth noting that the number of populations here is 6. The techniques we discussed early on for comparing two population proportions would not work here. If this die is fair, it should turn up any side for about 1 over 6 of the time. If this die is not fair, it should turn up to some sides more than the others. If the null is true, then our expectation would be that the die should turn up any side for about 1/6 of the time. What we want to test here is to compare the difference between this expectation with our observations using those 300 rolls. If there's a large difference between observations and expectation, the null is probably not true. If there's a small difference between observation and expectation, then the null is probably true. We will use the following table to measure the difference between observation and expectation. The observed frequencies were given to us in the example. The expected frequencies are just what we expect to get if the null is indeed true. If the null is true, we would expect 1/6 of 300 rolls would turn up to be side 1, that is 300 times 1 over 6, that is 50. We would also expect 50 rolls would turn up to be side 2, and 50 rolls to side 3, and so on and so forth. I would call the observed frequency column F with a subscript 0, and the expected frequency column F with a subscript E. The difference between FO and FE is just FO subtract FE. What we want to do in the next step is to sum up all the differences. Note that some of the differences here are positive and some of the differences are negative. To prevent the positive differences to be completely cancelled out by negative differences, a common practice to use squared differences. We would also need to scale the squared differences by the expected frequencies. that are FEs. With a little bit of calculations, we arrive to the last column of the table. That is, FO minus FE, take that square and divide it by FE. Summing up the last column, we will get a test statistic for this test, that is 9.8. This test statistic is a chi-square statistic, because this test is a chi-square test. In summary, the test statistic for a chi-square test is the sum of the square differences between FO and FE and divided by FE. I will discuss the characteristics of chi-square distributions on the next few slides. The chi-square distributions, like the t-distributions, also have this notion of degrees of freedom. The degrees of freedom for this test is the number of populations minus 1. That is 6 minus 1, 5. Therefore, the test statistic we obtain here is a chi-square statistic with 5 degrees of freedom, that is 9.8. This is a chi-square table. Several important properties of chi-square distributions are that chi-square distributions are characterized by their degrees of freedom, and this table is also ordered by degrees of freedom. The curve on the very top is not a symmetric curve, like a z-distribution or t-distribution. All chi-square statistics are non-negative values. The smallest chi-square statistic is 0. This is reasonable because it is the sum of square differences between observed frequencies and expected frequencies. On the table, only the upper-tailed probabilities are given. When we work on chi-square tests, we usually only deal with upper-tailed probabilities. Chi-square distributions are usually used to describe the difference or discrepancy between the observed and expected. In other words, it can be used to describe how good a model fits a set of observations, or the goodness of fit of a model. If the chi-square statistic is very small, meaning the discrepancy between what we observed and what we expected if the null is true is very small. That means we have a lot of evidence to support the null or little evidence to reject the null. On the other hand, if the chi-square statistic is large, this means there's a large discrepancy between what we observed and what we expected if the null is true. Therefore, we have a lot of evidence to reject the null. We are going to use this idea to evaluate whether the test statistic we obtained early on provides sufficient evidence to reject the null or fail to reject the null. We first use the critical value approach to solve this problem. The critical value for degrees of freedom 5 and alpha 0.05 is 11.070. Our test statistic is 9.8. Compared to the critical value, our test statistic 9.8 is closer to 0. Therefore, we do not have enough evidence to reject the null. Therefore, this die is a fair die, with equal probability of landing on each of these 6 sides. The p-value approach gives us the same conclusion. The p-value is the upper-tailed probability of the test statistic of 9.8. Using the chi-square table, we are able to find this p-value is going to be somewhere between 0.05 and 0.1, that is greater than alpha of 0.05. Again, we do not have enough evidence to reject the null. Example 2. Benson Manufacturing is considering ordered electronic components from 3 different suppliers. The suppliers may differ in terms of quality in that the proportion of defective components may differ among suppliers. To evaluate the proportion of defective components from the suppliers, Benson has requested a sample shipment from each supplier and obtained the following sample information. We would like to formulate a hypothesis that can be used to test for equal proportions of defective components provided by 3 suppliers. Using a 5% significance level, conduct a hypothesis test. What is the p-value? And what is your conclusion? The variable of interest in this example is the proportion of defective components from different suppliers. So we are analyzing categorical data. In this example, we are testing for equality of multiple population proportions. The number of populations we have here is 3. We will use the chi-square test for this example. But this chi-square test is slightly different from the previous die rolling example. The null and alternative can be set up this way. The null is that all the population proportions are equal. And the alternative is not all of them are going to be equal. In the null, PA, PB, PC are all equal, but we do not know what that probability is. So this is different from the die rolling example. In the die rolling example, we know that P1, P2, all the way to P6 is 1 over 6. Whereas here, we do not know what PA, PB, PC are equal to. In step 2, we would like to compute a test statistic for this chi-square test that involves summing up the squared differences between the observed and expected frequencies. The observed frequencies were given in the table. The expected frequencies are not as straightforward to find as the previous example. This is because we do not know what the values PA, PB, and PC are equal to in the null. In the die rolling example, we know that this probability is going to be 1 over 6. To find the expected frequency for each of the cells in the table, we need to find the row totals, column totals, and grand total first. The expected frequency for each cell is the corresponding row total times corresponding column total divided by the grand total. For example, the first cell, the number of defective components from A is the total number of components from A, multiply the total defective components from all suppliers divided by grand total. And that would give us 27.78. We work out the expected frequencies for the entire table. You may be able to see that I put the expected frequencies in a parenthesis to differentiate the expected counts with the observed counts. Once we figure out all the expected frequencies, we can use the same formula to compute the test statistic. That is, sum of the squared FO minus FE divided by FE. We get a chi-square statistic of 21.069. The degrees of freedom again is the number of population minus 1. That is 2 here. From the chi-square table, the p-value is the upper-tailed probability of 21.069, which is less than 0.005. Such a small p-value implies plenty of evidence to reject the null. We would be able to conclude the 3 suppliers do not provide equal proportions of defective components at 5% significance level.